In this video, I'm going to discuss with you the solution for quiz number 6. I'm going to show you some of your solutions and explains to you why they were wrong and how you can write a better solutions. Now, before we do that, let us recall the definition of a vector space. So suppose you have a set V with addition operations and scalar multiplications defined on it. And if all the objects in V satisfy all these 10 axioms, then we say that the set V equipped with these two operations form a vector space. Once you have vector space, elements that are in that vector space are going to be referred to as vectors. Now, for example, we have a set V. This is what we call the set builder notation, where you write down the elements of the sets here, and then you provide all the necessary descriptions for these elements right after this line. For example, in our case, our elements are the 3x1 column vectors, and the x, y, z are real numbers. So this is what we typically refer to as R3. Now, this set by itself cannot be a vector space, because for it to be a vector space, we have to define what are the addition operations and scalar multiplication. So just by itself, this is just a set. Now, once you have this set, if you define the addition operation this way, and you define the scalar multiplication this way, this is the usual addition definitions, and this is the usual scalar multiplications. Once you have this V, you can verify that all the objects in this R3 will satisfy all these 10 axioms, and therefore this V together with these two operations form a vector space. Now, the questions for today is, suppose you have a vector space V, and then you have a W, which is a subset of V. The question is, how do we know that this subset W is also a vector space? If you look at the Venn diagram, we have W sitting inside V. So V is given as a vector space. So it's going to be a set with two operations, addition operation and scalar multiplications. Question is, this subset together with that two operations, will this subset also form a vector space? Now, one way to answer these questions is to verify that all the objects in W also satisfy these 10 axioms. If you can do that, then W is really a vector space. And because it sits inside V, we say that W is a vector subspace of V, just to indicate that W is a subset of V. Now, because V is a vector space, that's given, so all these axioms that hold for all the elements in V will also hold for elements in W. So you don't really have to verify that all these axioms for W, because some of it hold for V will also hold for W. So you don't have to verify everything. Theorem 4.2.1 says that in order to verify whether or not W is a vector subspace of V, what you need to do is to check, number one, whether for any elements UV in this set W, will the additions U plus V also an element in this set W. You also need to check that for any real numbers and for any vectors, for any elements in W, whether or not your scalar multiplications KU will still be in this set W. There's a shorter way of saying this. Okay, this property here is saying that W is closed under additions. Okay, so W is closed under additions means that for any UV in this set, their additions is also in this set. This property here is also known as closed under scalar multiplications. So W is closed under scalar multiplications means that for any real numbers and for any elements in W, these scalar multiplications will still be in W. So theorem 4.2.1 says that in order to verify W, whether or not it's a vector space, you just have to check whether or not the addition is closed in W, and then the scalar multiplication, is it closed in W? Now, let us look at our questions again. So we have W1. Okay, W1 is a set of 3x1 column vectors with the first entry here has to be 0. Second entry be 2, and the third entry B3 can be any real numbers. Obviously, W1 is subset of R3. All these elements are elements in R3, so they are subset of R3. Question now is this a vector subspace of R3? So we have to verify whether or not the addition properties, W1 is closed under additions, and whether or not W1 is closed under scalar multiplications. Now, let us look at some of your solutions. So this is one of the solutions provided by students in our class. So it says that, it actually didn't really say a lot, okay? So I have to interpret what he's trying to say. So we have a vector u, we have a vector v. So the vector u apparently is b2, 0, 0. Vector v is b3, 0, 0. And then these additions give us b2 plus b3, and then we have 0 in the second component and 0 in the third component. And somehow this is in W1. Now, first of all, it doesn't really make sense. And this is actually something that is very problematic, because b2, 0, 0 is actually not in W1 if your b2 is not 0. You can also see the same thing. b3, 0, 0 is not in W1 if your b3 is not 0. So in fact, you are choosing two elements that is not in W1, and you claim that they are in W1, and you also claim that after you add them, they are still in W1. This is really not an element in W1 if your B2 and B3 is not 0. So this is extremely problematic. So this is extremely wrong. Let's look at another solutions. So in these solutions, the student says that step 1, we have to verify that W1 is not empty. And how the student does that is to give me one specific example. He says that, look, we have 0, 1, 1. 0, 1, 1 is an element in W1. 0, 1, 1 is really an element in W1. You can see that. Then therefore, W1 is not empty. That's perfectly fine. But here, the student says that, okay, let A be an element in W1, B in elements in W1, and A is given as 3 by 1 column vectors 0, 1, 2. B is given as a 3 by 1 column vectors 0, negative 1, negative 2. Now, A and B is really elements from W1, but if you really want to check the closure property and the closure property for additions, you cannot argue by giving me a specific example, because the properties actually require you to show that for all vectors, okay, in W1, if you add them, those two vectors are still going to be in W1. So once you give me a specific example, you are not going to be able to do that, because there are infinitely many specific examples you have to check. So you cannot really do that. So this is very problematic if you give me a specific example. Same thing here. This is again problematic. So once you have A and B, you add them and you get 0, 0, 0. And the student says that this is in R3. I mean, it's obviously in R3. 0, 0 is obviously in R3, but this is not what we want to say. We are not trying to say that A plus B is in R3. If you want to use that theorem, you have to show that A plus B is in W1, not in R3. So do not confuse with the spaces, because if you say that they are in R3, you are not using that theorem. It's like, yeah, obviously they are in R3. That is not what we want. Okay, so let's look at another solutions. So here, the student says that W1 is not empty, even though that particular student didn't justify why. And then the student also says that, let's say, vectors U is 0, AC is in W1. Vectors V is 0, DE, which is also an element in W1. This is true. And then the students do that computation and show me that vectors U plus vector B, V, is a 3 by 1 column vectors with 0 here, A plus D here, C plus E here, and then it's a stop. This is problematic in the sense that, yeah, so what happened to this? U plus V is this. So what is the conclusions? What can you say about this? What is this? Why are you doing these computations? Now, this is a 300 level math class, and I want you to know that making an argument cannot be simply like computations that looks like this. You have to make an argument. It will have to be in sentences. You will have to explain stuff. It is not enough to give me U and V and then the additions of U and V and let me fill in the blank. Okay, so this will not work. I do not understand what's going on. I do not know what is the significance of this computations. Okay, so how do you improve this? Well, okay, so first you have to verify that W1 is not empty. How do you verify something is not an empty set? Well, find an element in that set. If you can find an element in that set, obviously that set is not empty. So you can argue by example here, say that, hey, look, 0, 0, 0 is an element in W1. Therefore, W1 is not empty. The reason why we need this is because now we are going to pick elements in W1. So if W1 is an empty set, this will not happen, right? So now W1 is verified, it's not an empty set. So suppose I have two different elements from W1. Let's call it 0, B2, and B3. and then let's call another one 0, C2, and C3. Now, I make no particular assumptions on B2, B3, C2, C3. They are just any real numbers, okay? If I say that B3 is 0 or C3 has to be 1, then I am not making a general argument, okay? So 0, B2, and B3, and 0, C2, and C3, this is very important here. They are arbitrary real numbers. So these are arbitrary elements from W1. So if you take the sum of these two vectors, and you can see that the results that you have is 0, B2 plus C2, B3 plus C3, and this is in W1. This is in W1 because this is 0, and then this is a real number, and this is a real number. So this is in W1. This is what we want to show. It is in W1. It is also nice after you do this computation, you try to write a conclusions. Like, okay, what does this computation tell us? These computations tell us that W1 is closed under additions. Okay? So pick any real numbers. You cannot make a specific example of K. Okay? You cannot specify what K is. You just said K, let K be an arbitrary real numbers. Then look at what happened to these scalar multiplications. If you take an arbitrary real numbers, multiply with these 3 by 1 column vectors, this is by definition equals to the product K0, KB2, and KB3, and K0 is 0. So you end up getting 0, KB2, and KB3, which is again an element in W1. So you say that this is an element in W1. And then make a conclusion. It's like, okay, so what is this computation tells us? These computations tell us that W1 is closed under scalar multiplications. So once you have closed under additions, you have W1 closed under scalar multiplications, then by theorem 4.2.1, W1 is a vector subspace of R3, and make the conclusions. Sometimes if you forgot the numbering of the theorem, you don't have to do that. You can just say by theorem, W1 is a vector subspace of R3. So look, this is not just computations, it's with sentences. First, notice that what happens. Then you choose something, you let something from W1. And then it is clear that the sum is also in W1. Therefore, W1 is closed under additions. Full stop. Second argument, let K be any real numbers, then the scalar multiplication is this. It is in W1. Therefore, W1 is closed under scalar multiplication. Therefore, with the closure under addition and closure under scalar multiplications, W1 is a vector space by theorem 4.2.1. This is how you should make an argument at the 300 level linear algebra class.